Hello everyone. Today we are going to build the heterostructure of tin oxide and CNT, carbon nanotube. For this, we have a CIF file for tin oxide. Here we can see this, and we have a CIF for CNT. Here we can see it. This is a CNT that we have. So we will prepare a heterostructure of CNT and tin oxide. For this, first we will save this file as a VASP file. For this, go to export data, file, export data. Here, save it as VASP, tin oxide VASP, using Cartesian coordinates. Got this. Now, we will add the CNT, single wall carbon nanotube, into this. For this, we will go to edit data, phase, and we will import the CNT. Okay. So here we can see that we need to expand the unit cell so that complete CNT can be accumulated over the surface of tin oxide. So for this, we remove this. Okay, we have this. We will expand this. For this, we will go to edit data, or else we can see. We will go to edit data, unit cell, and transform. We'll transform this unit cell into 2 cross 1 cross 3. Okay. Here we have our unit cell transformed into 2 cross 3 cross 2 cross 1 cross 3. Okay, we'll save this as VASP file. So go to file, export data. We'll save this as VASP. So here we will have tin oxide SnO2 2 cross 1 cross 3. Save. Using Cartesian coordinates, we have this. So here we have 2 cross 1 cross 3. Yeah. Structure. We'll open this particular VASP file now. Here we have a VASP file, and now we will add our CNT into it. So for this, go to edit data, phases, here import, and we will import this our single wall carbon nanotube. Once we apply here, what we can see is this. Here it's overlapped with the tin oxide. We'll shift it upwards. So for this, go to edit data, phase. Here we will shift the CNT to the center of this particular unit cell, and here we can see it's in the A direction, so we will add approximately 2.5 the global coordinates. Sorry, did it to tin oxide. Here we will add it to CNT. And now, in order to shift upwards, here we can see it's in the B dimension or y-axis. So I will add it here, X. This looks good. Here we have our heterostructure, but this is not the one that we are going to use right now. We need to add vacuum to it. For this, first we will delete all the extra oxygen atoms that are outside the unit cell boundaries. So we'll delete all of this. Okay, rotate. Here we can see few more atoms, oxygen atoms present here. Okay, so here we can see there are no atoms outside the unit cell. We'll save this particular stratostructure as XYZ. So go to File, Export Data, and here we'll save this as XYZ file, and we'll rename this as inoxide SWNP hetero.xyz. No, and now what we need to do is we need to use these coordinates of this XYZ file and edit our initial tin oxide VASP file that we have saved. So for this, we'll open our tin oxide VASP file here and we'll copy this and add it to a new file. Here it's SnO2-CNT. There's something that's left here. Oh, even this line is left to be copied. So I'll copy it once again. So here we have this file. We have pasted this particular coordinates here, and now we'll open our SWCNT. Sorry, it's CNT. So I will open this. Open this file, particular file, and paste this coordinates into Excel file using text import wizard. So here we have this. There's slight shift in this. So we'll correct this. Now we need to calculate the total number of tin, carbon, and oxygen atoms present here. And before that, I will change this to decimal number 6 so that all numbers look uniform. Now the number of tin atoms, oxygen atoms, and carbon atoms, here we have tin. Total number of tin atoms here we can see is 30. Total number of oxygen atoms, here we'll change this to general. Okay. Total number of oxygen atoms, it starts from 31 and ends at 58. So there are 28 oxygen atoms. And here we can see the total number of atoms that we had initially in this particular XYZ files is 130. So we can have it 130 minus 30 minus 28, which is equal to 72. So we can use this. I'll copy this and I will paste it into our new file that we have here. Okay. Also, I will rename it as SWCNT. Okay. And now, what we need to do is we need to copy the coordinates. So for this, I'll first delete this names or labels of the atoms, and copy and go to our file paste. Here, as we know, we have this is the tin oxide CF file, and we have created a supercell of 2 cross 1 cross 3. So we need to multiply it by twice or 2. So copy this here, paste twice. So this is the new coordinate that we have. Second, here I'll copy this, paste into 3, which is equal to this. We'll slightly increase this so that the atoms or the structure would be well spaced, or there's a lattice mismatch between the CNT and tin oxide, and to compensate that, I'll add 0.2 there. And now we need to add vacuum to the B axis, that as we can see here, it's the B axis wherein we need to add vacuum. So here I'll add vacuum of 16 approximately, 16 Armstrong. It would be approximately 20 here. Now I will save this file as hetero.vasp. Now here we will open the saved file. So for this, go to open, saved our VASP, open our VASP file. Here we can see how we have built our heterostructure. We can expand this by going to boundaries, and here I'll expand it thrice in the x dimension. Okay. So here we have our CNT tin oxide heterostructure form. We can use this particular heterostructure for calculations, and we can get the optimized heterostructure by DFT calculations. So thank you for watching this video, and also subscribe our channel to watch more such videos. Thank you.